Hello, welcome to the next video lecture on strength of materials.
On the screen you can see there are different examples of torsion loading. You can see automotive powertrain where a shaft that transmits power from engine to the rear wheels is subjected to torsion. And you can see a screwdriver. When you use screwdriver to turn screws, you are actually applying torque on the screwdriver. And even when you twist the cloth, when you want to remove water from it, you're applying twisting movement there. It is also torsion. And if you look at this example, there is a shaft which connects turbine and the generator. This is the generator and this is the turbine. To separately analyze these three entities, generator, shaft, and the turbine. The central part is called shaft. Normally shafts are circular in nature. When the power transmission happens from here to here, there will be a torque applied on this shaft which will be equal and opposite. This is another example of shaft. And you can see this example, it is a cantilever rod fixed here and you are attaching one more rod here, maybe to welding, and you are applying P2 here and P2 here, which are separated by a distance D2, but they are equal and opposite load. It is actually a couple. It tries to apply a moment here. It tries to twist this object. So P1, P1 or P2, P2, whatever you are seeing there, they are actually forming a torque. And the magnitude of the torque will be equal to P, the load, into perpendicular distance between the loads. T1 is equal to P1 into D1 is a torque there. That it is clockwise torque. But P2, P2 when you consider, it is supported by a distance D2 and that is actually counterclockwise torque. These are some of the examples of torsion. Shaft is a straight rotating member which is mainly for power transmission. This twisting movement is also called as torque. A shaft, when subjected to only torsion and not accompanied by any other forces or moments, is known as pure torsion. First assumption is material is homogeneous. It is elastic property is same throughout the volume. Second assumption is it obeys Hooke's law. In case of shafts, shear stress is developed. So shear stress will be proportional to shear strength gamma, or the proportionality constant here is called as G. So tau is equal to G into gamma, where G is called modulus of rigidity of the material. Cross-sectional area should be plane. Cross-section of the shaft should be a planar section. Circular section should be circular before and after loading. Every diameter of the material should rotate through the same angle, means angle of twist is same. The stress of the material should not exceed the elastic limit, means the loading happens within the elastic limit. These are the assumptions that we make before deriving the torsion equation. Now we will go to torsion equation, a very famous equation for all the shaft design. This equation is required. Torsion equation, this is very, very important. So we'll try to derive this equation now. Before deriving, let us consider a shaft which undergoes twisting. Just observe these two sketches. The very first sketch, you can see a shaft and the points A and B are actually representing a horizontal line on the surface of the shaft. Point A is the point on the circumference of the cross section here. Point B is the corresponding point on the fixed end. So AB is actually representing the length of the shaft. So let us say length of the shaft is L. Now, when I apply torque T, you see a red color arrow here that represents the torque T. When I twist the shaft, since the end at point B is fixed, it will not move there. But the point A will get rotated. The new location, let us say it is A dash. If I call this center point as O, the line OA is actually representing the radius of the cross section, and OA dash also is another radius. OA has rotated to OA dash, and the angle through which it rotates, let us call it as theta here. That angle I am calling it as theta. This angle made by A dash, the angle made by A dash is a shear strength. It is represented by gamma. In the examination, when you are deriving this equation, you don't have to draw this 3D sketch, but the same can be represented in 2D also. This rectangle represents the front view of this shaft, and I'll show axis also here. And in the side view, it looks like this. I will draw a circle. This is the side view. This is the projector. And let us say it is fixed at this end. And let us call the length of the shaft as L. Let us consider the point A here and point A here. This is the front view of A, this is the side view of A. And when I draw the center for this section, I can call the point O also here. I'll call this as point B. A and B are on the circumference of the shaft. Let us say I'll apply the torque like this. Torque is nothing but twisting moment. I call this as T. When I apply the torque T, what happens? The line BA gets rotated. Just like I showed here in the 3D sketch, the point A gets shifted to some new location here. Let us say it rotates here. New location of the point. I'll call this point as A dash. This is in the front view. In the side view also, I can locate the same point. It comes here. And if I join this A dash to O, that is actually radius. So let us call this radius as R. And the diameter of the shaft, let us call it as capital D. Now, this angle through which it rotates in the side view called theta. It is called as angle of twist. And this angle here, the angle A dash, this is called shear strain, gamma. Now, I am applying torque on the right end, but since I am fixing the left end, there also opposite torque will be developed as a reaction. I'm applying torque, maybe clockwise torque in the right hand side. So anti-clockwise resisting torque will be developed automatically at point B. So it is as good as subjecting the shaft to two different moments on either ends, equal and opposite. So L is the length of the shaft, R is the radius of the shaft, theta is called angle of twist, normally in radians, gamma is shear strain, T is the applied torque, tau is a shear stress, and G is a modulus of rigidity of the material. These are the symbols that I am going to use in this derivation. First, let us calculate gamma. From the trigonometry, if I say tan gamma is equal to A dash divided by AB. A dash is a right angle triangle. Gamma is the angle that I want to find out. So I'll consider tan gamma, which will be A dash by AB. But for small angles, tan gamma can be written as gamma AB. Or AB is nothing but length L. AB is length of the shaft. So I'll write it as L. If A dash in the front view and side view can be equal, A dash in the side view is an arc. And arc A dash can be found out easily by multiplying R into theta. Right? It's a sector length. Sector length is radius into sector angle. So from the side view, A dash is equal to R into theta. So we will use this result in gamma equation. So therefore, gamma is equal to R into theta by L. This is one of the result. But we know the Hooke's law. From Hooke's law, shear stress is equal to G into gamma. Or if I take tau by gamma, it becomes G is equal to tau by gamma. But gamma is R theta by L. I'll substitute that. So tau divided by R theta by L. Or I can rewrite this. I can just rearrange these terms and write it as tau by R is equal to G theta by L. What is tau here? Tau is actually shear stress at outermost layer. Means at radius R, this is the shear stress. It is also said that shear stress is 0 at the center when R is equal to 0, and it is maximum at outermost fiber, and it varies linearly. We'll write that here. If small q is the shear stress at any radius R, then I can write tau by R is equal to Q by R is equal to G theta by L, because shear stress varies linearly with radius R. And if you want only Q, which can be written as tau by R into small r. Since shear stress varies linearly, I can find out shear stress at any radius R. Outermost fiber shear stress is tau, but any other radius it is Q, and that can be found out using this equation. This is one part of the derivation. We'll do the next part. I'll call this equation as equation 1. Now I'll take the cross section of this shaft. I'll consider the cross section. This is the cross section. It is of radius R. I will take elemental ring in this area at a distance of small r. Small elemental ring I am considering at a distance of small r, and thickness of this element I'll call it as dr. If I can find out what is the torque at this ring, I can find out what is the torque for the entire cross section by integrating it between the limit 0 to capital R. That's why I'm considering this. Now at radius R, small q is a shear stress. We just now put the equation for that. Maximum shear stress is tau, which happens at radius capital R. Now we will consider the area of this elemental ring. Consider an elemental ring as shown. The area of this ring, I'll call it as dA. And this ring, it is actually a annulus circle. If I cut open this ring and make it a rectangle, it is actually a small rectangle of this dimension dr and this dimension equal to the perimeter, which will be 2 pi r. So I can write dA as 2 pi r dr. And we know that small q is equal to tau by capital R into small r. So I can find out what is the shear force here. Shear force in this element, call it as dF, because it's a very small differential element. But shear force is what? Shear stress into area. Shear stress into area. Shear stress in the elemental ring is Q. Q into dA. And Q is obtained as tau by R into R. And dA is 2 pi R into dr. And this is nothing but tau by R into R square into 2 pi into dr. This is what? This is the shear force in this element. When I know shear force, I can calculate what is torque. If I multiply force into perpendicular distance, I will get the torque. So torque in the element, call it as dt. dt is equal to df into perpendicular distance. Force will be acting like this radius r. This is actually df. df into perpendicular distance is r. So I have to multiply this with r. So dt is equal to df is what? Tau by r into r square into 2 pi into dr. This is df. Into the perpendicular distance means r. This is the torque in the element. We are talking about a small elemental ring, remember, for which we got the torque like this. Now I want the total torque. I have to integrate this expression between the limit 0 to capital R. So total torque in the shaft is T is equal to integral dt. So that is equal to integration from 0 to capital R. This dt is what? Tau divided by R into, see, 2 pi into R square into R, which is 2 pi R cube dr. Now in this, I can take tau, R and 2 pi outside because they are constants. And when you integrate R cube, it becomes R power 4 by 4. I'm substituting the limits also. And this can be written as tau by R into 2 pi R power 4 by 4. Or I can cancel one of the two here. This is what it becomes. So, and this pi R power 4 by 2 is nothing but polar moment of inertia. It's called J. Tau by R into J. And this is called polar moment of inertia. I will write it separately, where J is equal to pi R power 4 by 2, or if I substitute R is equal to D by 2, because radius is diameter by 2, D by 2 whole power 4 divided by 2, you will get it as pi D to the power 4 divided by 32. It's called polar moment of inertia, or it is sometimes called as J suffix PR. JP stands for polar moment of inertia. And this equation can be written now like this. T by J is equal to T by JP, or J is equal to tau by R. This is the second result that we got. This I am calling it as equation 2. Now observe equation 1. Equation 1 was tau by R is equal to J theta by L. Now tau by R is equal to T by J. Now we can combine these two. So combining equations 1 and 2, we can write T by J is equal to G theta by L is equal to tau by R. This is called torsion equation for solid shaft. Now what will happen if it is a hollow shaft? If we consider a hollow shaft, what will happen? What are the differences that you get? If it is a hollow shaft, then here this would have been R naught into theta. because r naught is the outer radius. Inner radius will be ri. So it will be r naught into theta, and this would have been r naught theta by L, and this equation would have been tau by r naught is equal to g theta by L. Okay, so tau by r naught you would have got if it is hollow section, and here you should have integrated it with ri to ro, between the limits ri to ro. So you would have got J is equal to pi do power 4 minus di power 4 divided by 32. So I will write the result here for hollow section, or for hollow cross section. The hollow cross section will be like this. This is the hollow cross section, and I'll call this inner radius as Ri and outer radius as Ro, or in terms of diameter it is called Di and Do. So then what happens? This equation would have been T by J is equal to G theta by L is equal to tau by R naught. This would have been the torsion equation, with J is equal to pi d naught power 4 minus di power 4 divided by 32. I can show you how these shear stress distribution occurs in the cross section. Shear stress distribution. If it is a solid shaft like this is a solid shaft, and for hollow shaft also I will write. Let us say this is the hollow shaft. Now I'll take the reference line here at the axis, and if you want to draw the shear stress distribution, it will be maximum at the outermost fiber. Shear stress will be maximum here, and it will be 0 here. At the center it will be 0, and you know that the variation is linear, so it will be like this. So this is how you can show the distribution of shear stress in a cross section or hollow sections. In hollow sections, what happens? This is the center, and again outermost fiber you will have maximum shear stress, and it will have 0 value at the center. You can show it like this, but shear stress will be present only in this region, so I have to show arrows only from this point. Okay, this is how shear stress will be distributed. This is tau. This is solid shaft, this is hollow shaft. So shear stress distribution will be linear. Next, I will give the equation for some of the definitions that we come across. One of the definition is called polar section modulus. First one is called polar section modulus. Polar section modulus is nothing but the ratio of polar moment of inertia J and the outermost radius. It is called as Zp, denoted by the letter Zp. And this Zp is actually the ratio of J, polar moment of inertia, to the outer radius. And moment of inertia about the axis perpendicular to the plane of the area is known as polar moment of inertia J. And in torsion equation, T by J, torsion equation is T by J is equal to tau by R is equal to d theta by L. This gives us T is equal to tau into J by R, or it is tau into J by R is called Zp, polar section modulus. So polar section modulus Zp is the ratio of polar moment of inertia J to the radial distance to the outermost surface of the shaft. Now if you take the same definition for solid shaft, if you take, Zp is equal to J by R, but for solid shaft J is what? Pi into e to the power 4 by 32, and R is what? It is d by 2. Now if you cancel one of the d here, it becomes pi into d cube by 16. This is the polar section modulus for a solid shaft. For hollow shaft, Zp definition is what? J by R. But for hollow shaft, the polar section modulus is pi d naught power 4 minus di power 4 divided by 32, and R is actually R naught. Outermost radius is R naught. So R naught is nothing but d naught by 2. I'll take d naught power 4 outside. It becomes 1 minus di power 4 divided by d naught power 4 in the bracket, divided by, here it will be 16 d naught. Now 1 d naught if you cancel, becomes pi d naught cube into 1 minus k power 4. The ratio is called k, 16, where k is called di by d naught, the ratio of diameters. So this is what you get for a hollow shaft.